Hi everyone. On today's video we're going to be having a look at Altair Inspire 2020.1 where we're going to be performing an analysis and an optimization of an aircraft door support fitting. So let's begin. To bring in the file we can either use Open or go to File, Import, locate to the directory where you've saved the file and press Open. So here it is. Now just a couple of controls for you. So to rotate the model is to middle click on the mouse. So using the scroll, clicking the scroll button, or to pan we can right click on the mouse, and to zoom in and out is obviously just the scroll button. So now that's done, let's go ahead and assign some material properties. So there's a couple of ways in which we can do this. We can do it through the property editor or interactively on screen. So if you haven't got the model browser or the property editor showing, you can go into view and choose model browser and property editor from here. So if we left click on the part, we can see that in the property editor we have things like some general properties like the name of the part, the material. We have also some meshing controls within here that you can choose, motion controls, etc. But at the moment we'll just focus on changing the material. So we can either do it within here, or if we right click on the part itself and go to material, then aluminium 2024, we'll select that and just left click somewhere else on screen, and that's it done. And we can even press this button here to calculate the mass of the part. Another thing that we could do is actually bring in our own material properties if you happen to have them. So we have this in the structures ribbon, we have the materials tab. So you can see there are a couple of materials in here. We can obviously delete them using this button, and to introduce a new one we just press the plus. We can change the name, put in the Young's modulus, Poisson's ratio, etc. to create a host of material properties. Basically you can create your own material database, save it, share it around, and open it up so that you only need to create this material database once. But for today we'll stick with aluminium 2024. So now that that's done, let's have a look at some geometry editing capabilities. So within Inspire, more often than not you may bring in your CAD and the CAD will be fine, but if you do want to make really quick design changes and reanalyze them really quickly, we can do that using the geometry editing tools in here. So we'll just for the moment create something simple like a rectangle by center. So we can click on that and then choose the plane which we want to draw on. So let's just say this top plane for the moment, and we'll create a new part. And we can also snap normal to the grid and then just left click and drag to form the rectangle. So we can right click and swipe to confirm that sketch, and then right click and swipe to confirm that again, and it's now created a surface for us. What it's also done is to activate the sort of extrude tool that we have called push pull. So this is already active, and we can select this here, and just by left clicking and dragging we can choose how high we want to drag it, and obviously we can equally put it in the height. So let's say we go 0.04 for example. So yeah, that's pretty interactive to create that part. One thing you notice is we're in meters. Obviously if you want to change that you can go to the bottom right hand corner and just choose whatever unit system you would like to work in. So that's just a quick demonstration of some of the things that we can do. Obviously we don't really want this, so what we can do is left click on the part and just press delete. So that's just some of the sketching functionalities. Another nice tool is if you notice that there are any dodgy surfaces around in the model, you could go ahead and delete them and then repatch them within here. So for example, if I go on the patch tool, I could patch this surface. So click once to sort of initiate the action, and then click again to patch that surface. So you can see that we've closed off that side. We can actually delete the surfaces too with this tool, so you can see that we have this X next to the mouse. So if I just click on that again, that'll get rid of it. So left clicking to come out of the patch tool, we can now have a look at some of the tools in the modify section. So without having to create a sketch, we can edit the geometry that we already have. So for example, using the push pull tool, we can say increase the width of this, so we can just left click and drag interactively. You'll notice that it snaps, so if it does, if you press Alt on your keyboard, that will disable the snaps. If you realize that you've made a mistake, you can always just Control Z to revert back to the original design. Other things that we can do, for example, if you realize that there's a bolt hole in the wrong place, for example, we can left click and we can just interactively click and drag and move the holes into their correct position. So again, we'll Control Z out of that one. Another nice little tool is the mirror function. So we can mirror this part, let's say around this plane, and we can keep the original and we can instance it as well. So when we instance it and we perform some geometric changes on the original part, we can go to push pull, say I click on this face, and if I hold down Alt again, you'll see that both parts will have that change added automatically. So that's another really quick way to get through some design changes rapidly. So we'll edit undo through that, as we only want to consider the one part. And within here as well, we have Boolean tools when you have more than one part, cutting tools where we can easily just assign a cut plane throughout the part and split it into two. And then again, we can go into Boolean and combine the two, again, just to show how this works. You can see that it's left an imprint, so we have some simplifying tools where we have an imprint itself, so it's noticed those imprints that we've just created, and we can go ahead and just remove them. And again, we have tools for removing rounds, removing holes, and a plug tool. So holes and plug are pretty similar. So a hole will find the hole and it will just simply remove everything within there. So this is something that we'll do for the optimization in a bit. And that will sort of fill the hole and Boolean everything together. Whereas if we were to plug it, we can double click on this, it finds everything adjacent, and it creates a separate part as a plug. So they do the same thing, just plug will not Boolean the parts together. Other things that we'll do for the optimization is we can partition areas. So for the optimization, we'll need to come up with some design spaces in areas which the optimizer can't touch, and that we'll do with the partition tool. And finally, we have mid-surfacing and creating fillets and chamfers. Another nice thing that we can have a look at is, so obviously we can cycle through the ribbons at the top, so everything's in sort of a left to right workflow. But another thing that we can do is we can access the tool belt. So if you press Alt and right click, you'll bring up this tool belt, and that will give you access to a lot of the tools just from this one click, so you don't have to jump between ribbons. And we have, so just Alt will bring up this set of tools, so a lot of the geometry editing is within here, plus some structural analysis boundary conditions. If we press Control, we get more of the inspire motion side of things. If we press, so that's Alt and Control, if we do Alt and Shift, we get more of the structural analysis side, and we can do Alt, Shift and Control, and that will give you some Polynomials functions. So there's two ways you can access the tools, either using the tool belt, which is Alt and right click, and then a combination of Alt, Control and Shift, or we can just use the ribbons. So now that we've done that, let's go ahead and start the analysis. So bearing in mind here that we're going to do an optimization, we're going to actually partition the part before we run the analysis. So we'll go to the partition tool. It notifies areas where it thinks to put in a partition, but we're going to manually create them ourselves. So we can zoom in and we can click on, you can see it's highlighted this cylinder, so we can left click on it once to highlight the area which we wish to partition, and then left click on it again, and it will create our partition of 3 mil. Now we're going to do the same, so left click, then left click again around these bottom 6 fixings. So we'll repeat that, and then we'll do one for where we're going to apply the force. But actually this is going to be 5 mil, so we can just type in 0.005, hit enter, and that's the partitions created. And you'll see once we right click and swipe out of here, you can see that it's created these different partitions in the model browser. They'll have the same material properties too, so if we click on that, we can see that it's aluminium 2024. So now that we've done that, we can go ahead and start setting up the boundary conditions for the model. So we'll go ahead and go to structure. So what we can do within here is we can apply fasteners and joints automatically. So it will look for through holes or single holes, for example, and apply the FE definition to these areas. We can apply connectors and spot welds, for example, and even contacts too. So because we have 8 odd different parts here, we can click on the contacts tool and you can see that all the parts are seen as bonded together, which is fine for the analysis that we're going to run. So just a quick example again. So for fasteners, we can look for aligned holes or single holes, for example, and it can notify regions which you would like to fill, and then we can just left click and it will automatically put in something in there. Obviously, this isn't what we want to do, but that's just a brief example of how it can work. So we'll undo that and come out of there. So let's go ahead and start setting up the analysis. So I'm going to go ahead and apply some supports. So one thing you'll notice is that we actually have multi-purpose function buttons within Inspire. So within the Loads tab, you'll see that we whatever area is highlighted in blue is the action that you're going to perform. So in this case, it's supports, but we can also do pressure, torques, forces, for example. And the same is for other tools as well. So you can see in the displacement side, we have displacement constraints and we have enforced displacements. But we're looking at creating some supports. So we're going to left click on support and let's just rotate the model so we can see beneath it. Now, when it comes to applying the support, you'll notice that if you look just to the right of the mouse, you'll see sort of what the support is going to be applied to. So in this case, you see sort of the rectangle above the support. It means it's going to apply it to a face. If we move the mouse to an edge, you can see that the rectangles become just a line. So that's an edge support. And if we move into the center of here, we can see that it's going to put in a support within the cylinder itself. So this is the one that we're looking for. So once you can see that symbol, we can left click and the support will be created. You'll also see a load case is now created too. So we'll go ahead and do this for the bottom 6 supports. So just left click within the cylinder. And those are the supports created. Another thing that we now need to do is to apply a force. So we'll change this to force. And let's select the center of this point here. So we'll go for a value of positive y. So we can either change the direction by pressing y, so you can see this arrow switching, and we can use the plus minus tool here as well. So let's say 1000 newtons, for example. So we'll right click and swipe to select that. So that's basically one load case now done. But we'd like 2 load cases for in this case. So you can see here that in the model browser we have all the loads and displacements, and then we have the one particular load case. So let's we can go ahead and rename this to positive y. And now we want to create another load case. So to do that, we can right click on positive y and go to new load case, and we'll call this positive z. Now, without having to create everything again, because we have most of the parts here, what we can do is move from the All Loads and Displacements tab. So Inspire works in a couple of different ways. If you were to left click on support 1 and hold down shift and go to support 6 and left click again, if we click and drag to positive z, it will copy and paste all the supports. But if we were to do it from positive y, it'll actually move them. So you can see force 1 here just to demonstrate. If I click force 1 into positive z, it will move from one load case to the other. But when we want to copy it, so if we want to copy any supports, forces, any boundary conditions, we take them from all loads and displacements. If you want to move them, make sure you move it from one load case to the other. But now we can see that the positive z load case is written in bold, which means it's active. So anything that we create here is going to go into this load case. So let's apply another force within the center of here. Let's go to positive z, and let's make this, for example, just 2000 newtons. Okay. So in its simplest, that is the boundary condition setup complete, and we can go ahead and actually run the analysis. So we'll press this play button here to run an OptiStruct analysis. So OptiStruct being Altair's implicit FE solver. So we can change the name, so tool support, and we can chuck in an analysis as well if we want. The element size, now you can override the element size if you want, but Inspire will come up with an element size that it deems suitable for the geometry that you have. So you can leave that, or you can override it if you want to perform any sort of mesh sensitivity studies. Other things that we can do are normal modes analysis, buckling modes. We can choose speed and accuracy. So in this case, we'll just run with faster to help speed up the solve time. And again, for contacts, we can do sliding only and sliding with separation. Now, sliding with separation will take a little bit longer to solve. We can include gravity, and also we can include and exclude different load cases. So from here, we can go ahead and press run. One thing that you might want to do before that is if you go into File, Preferences, and go into Run Options, you can choose the number of CPU cores that you would like to use. So obviously, use as many as you have available. So yes, press run. It may take a matter of 2 to 3 minutes. So in a second, I'll make some results magically appear. So once the analysis is run, you'll see that the parts now have changed with this little contour appearing next to them. So that means that these parts have got results loaded, and you should see a green tick around this region here indicating the results are there. To actually see the results, you can press the green tick or just click on this button here, and we can have a look at some of the results. So in this case, we're just having a look at displacement. We can change the contour. So if we press this, legend options button here, we can choose the legend colors, and we can change displacement, let's say, to just rainbow. So we'll press OK on that one. And here we can see the displacement values for the different load cases, so positive Y, positive Z, and a result envelope, which is sort of the max of the two. So we can see displacement. Other result types are, we have factor of safety, so you can see here the minimum is 10, and it goes up quite high to roughly 8,000. And we can have a look at things like percent of yield, von Mises stress, for example. And there's even a slider where we can identify the regions of highest stress, and you can see here that it's at the front of the mounting regions here. Other things that we can do, say if I pop back to displacement, is we can actually run the animation. So we can choose the speed. If we go to positive Y or positive Z, we can run the animation. So only available for those two instead of the result envelope. And we can change the amount of deflection, we can change the speed of the animation, we can show the original shape, we can choose to show the boundary conditions, show the max deformation, and we can even hide the contour too. One nice thing, again, when it comes to particularly comparing different designs, is we have this min-max function. So this just plots a call out on the nodes with the maximum and minimum values of the contour that you have showing. So we can find the minimum displacement around here and the maximum on the parts as well. And if there are any points of interest within the model, we can just drop callouts anywhere across. So we have obviously the corner, but we can choose to drop one there and one at this point as well, and you can interactively see the displacement across the whole part. There's even a callout table, so you can identify all the different callouts within here and see what the values are. So we'll appear out of that, and we'll come out of the results too. So now that we've run the analysis, for example, we could see that the factor of safety, the minimum was 10. So if we're looking to optimize the part, there's a couple of things that we can do. So we'll look in this case at a couple, so we can optimize for maximizing the stiffness or for minimizing the mass. So a way of reducing the weight of the part, but still either maintaining the deflection of the part or minimizing the deflection, or allowing a little bit of deflection whilst reducing the amount of material of the part. So that's basically maximize stiffness and minimize mass respectively. So the first thing that we need to do is we need to actually defeature the part. So what we want to do is give the optimizer the most amount of space possible to find the optimal load paths. So the more we constrain the optimizer with the amount of material available, the more difficult it will be to find these optimal load paths. So the first thing we're going to do is we're going to defeature the part. So we can go back into the geometry tab, and in this case we're going to go to simplify, and we're just going to use the holes tool. So we've already done the partitions. These aren't the holes that we wish to fill, so we can press this clear button here, and we'll manually go ahead and just delete the holes. So in this case it's quite simple. So all we need to do is we have this back face here. If we double click on it, it will identify all the adjacent faces. So we double click, it's highlighted all these in red. If we left click again, it will just fill the hole. Now we can do the same on all these parts. So I'll rotate around here, double click again, and cover it. And we can also square off these faces as well, and we can use the hole tool to do that. So if I left click and then left click again, so if you double click it will try and highlight everything. So if you do a left click, wait a second or two, just move the mouse and left click again, it will square off the part. So we'll do that here as well. So in essence, I mean, this is a reasonably simple part, but that's our design space created. So now that we've created the geometry of it, we actually need to assign the design space. And again, that's quite easy. You can either do it in the property editor here, or you can right click on it and click on the design space too. So now that we've done that, let's go ahead and set up some optimization constraints. So there's a big emphasis in Inspire in making sure that the part that you optimize can actually be manufactured. So more often than not, you're not going to want to 3D print everything, and that tends to be maybe a misconception of the parts that you're always going to be left with after an optimization, and obviously that's particularly difficult to do. So what we have within here is we have a set of shape controls, whereby we can set mirror planes or symmetric controls and some draw directions, for example. So depending on the manufacturing technique, we can put a single draw, split draw, extrusion, and even overhang constraints if you are to 3D print the part. In this case, we're just going to apply a symmetric control. So we're going to click on the part here, and as all planes are highlighted in red, we just want to keep the one in the ZX plane. So we can left click on this plane, left click on this plane, and that will deselect it. So we're left with just plane 2 here. So now that that's been assigned, we can go ahead and run the optimization. So let's have a look at what we have within here. So we can rename it. So in this case, it could be maximize stiffness, or you can call it minimize mass, whatever it may be. We have several different types. So we have topology optimization, topography and gauge, lattice, and even polynub shape. But today we'll just focus on topology with two different objectives. So we've got maximize stiffness that we're going to have a look at results for, and minimize mass. There is also maximize frequency in there. So for maximize stiffness, you can see that we can set some mass targets. So we'll look at keeping sort of 30% of the total design space volume. Or if we were to look at minimizing mass, whereby we're likely to remove obviously more material, but that's going to lead to a greater deflection, we can set a stress constraint as a minimum safety factor. So in this case, we'll have a look at one for 1.5. We can set frequency constraints within the model. We can set thickness constraints, so we don't want members to appear particularly thin, as it's likely to lead to failure. So we can set a minimum constraint on that. Again, same with faster and more accurate, so we'll stay with faster. You'll only really use more accurate when you're sort of at a validation stage. And again, same with contacts. We'll keep that as sliding only. So we'll go ahead and run that. This will take a little bit longer, say maybe 10 odd minutes. So in a sec, we'll go ahead and have a look at some optimization results. Once we run the optimization, we should come to a screen that looks something like what we have here with the Shape Explorer shown. So typically when it comes to running a minimized mass, the more optimal shape tends to be towards the right hand side of the slider, so we tend to have to add some material. So the slider should appear around this range, and we can obviously start to reduce material, but we can see that the structures are now disconnected. Or if we move to the right, we'll start adding material, and just again having a look by eye, you can see that some of the members are looking a little bit thin. So we can just move this to the right a little bit as well. And now we can see we've got a more complete structure here. So what we've actually done is we've run an optimization for maximizing stiffness and for minimizing mass. So we can have a look at the maximize stiffness run, and you can see that the results are very, very different. And obviously they're likely to weigh very different as well. So again, here we can perform the same thing in adding or removing material. For a maximize stiffness run, the best result tends to be around the middle anyway. But again, if we move the slider, we can see that we can remove material and then land on a value that we think looks acceptable. So focusing on the minimized mass, what we'll do is we'll actually from here is we will reanalyze the part. So we've run the optimization, it's provided us this this shape here, but really what we want to do is actually confirm that the performance is indeed better. So if we sort of calculate the weight of the part, we can see that it's sort of 0.08 kilos. Whereas if we switch to the original part, it was 2.8. So obviously we've lost quite a lot of mass. So let's reanalyze. So just by pressing that button, we can continue the reanalysis. So we'll let OptiStruct take over again, and in a second we'll be able to have a look at some of the results. So once the analysis or the reanalysis is complete, we can have a look at the results. So we'll just press this green tick up here to have a look at the results. So we get the same for the two different load cases, and we'll have the result envelope in there. So we can play the animation, check the displacement again. So we have the same contours as before, so we can look at things like a factor of safety, and we can see the minimum here is 1. And again, we can identify the regions of lower factor of safety using the slider as well. Again, we can query the same result types as before. So what we will do again is we'll plot a minimum and maximum value. So we can see the minimum of 0 and a maximum of, again, 6e to the minus 4 meters, so still very small displacement indeed. And the nice thing that we can do is actually we can go ahead and compare some results. So if we press the compare results button, what this will bring up is a table of results for both the original analyzed part and the optimizations. So for example, if you can see in this table here, we can see a result envelope value, the positive y and z load cases, and you can see here that the maximum displacement is obviously a lot smaller for the part that has a lot more material to it, but you can see that the mass has dropped from almost 1.5 kilos to, well, a tenth of that size. What we can do as well is we can bring in some more contours within here, so we can plot obviously displacement, minimum and maximum. We can put in factor of safety, so let's say minimum factor of safety. Obviously you can see that it's a lot higher for the part with more material, but as expected, because we've done a minimized mass run, so you're going to have more deflection within your part here. And we can do the same for all these different outputs. So this is just a really quick way to compare the your design before the optimization and after, and obviously based on the criteria that you've set, you can see if this is acceptable or not. And you can do the same for the optimization for max stiffness just by performing a reanalysis on the optimization for max stiffness. So if we come out of this, we can change this with the radio button here to optimization for max stiffness, and you can go back into the optimize tool here and press, well, if we go move that to the center again and press analyze, and then we'll be able to compare all the parts. So you can really sort of dig into a generative design process by trying all these different designs, different optimizations, and seeing which one suits your purpose the best. So now that we've done that, actually, so we've confirmed the results and we're happy with the performance of the part. So what we're going to do is we're going to actually create something that we can bring back into CAD. So obviously what we're looking at really at the moment is sort of like a mesh element density contour. But really what we would like is some CAD surfaces to either reanalyze again if you need to, or take into CAD. So there's a few ways of doing that. So one of the first ones that you can see here is we have a fit polynomials button. So these is just going to wrap polynomials, so these sort of polynomial blocks, and it will fill the part with these. So these are all editable. But for more complex shapes, it's sometimes easier just to use this tool to automatically sort of wrap the shape for you. So if I just press fit polynomials, you can see that it will take us to the polynomials ribbon, and it's created the fit for us. So we can right click and swipe out of that. It will exit the polynomials tool, and it will create a new part for us. So you can see here that if we hide off this optimized part, we're left with this series of polynomial cages put together that you can go ahead and just file export. Or what you may wish to do is obviously edit the polynomial cages such that they conform to the fixings a little bit better than what's shown at the moment. One thing, again, to immediately notice, which could be of help, is that you can see that two of the fixings are redundant. So that's a really quick design change and way to reduce weight even further. You can see that sort of these two either side aren't necessary based on the minimized mass run. So that's one way we can do it. Another way, if I bring back the mesh element sort of contour, so the original design space, is to manually wrap the shape. So again, I'll just briefly demonstrate how we can do that. So if I go into the wrap tool, and you can see here that what we can do is see sort of a visualization of what will be wrapped. So depending on where the mouse is how the wrap will appear. So if I just click somewhere on this beam and move upwards, so you can see that where I position my mouse sort of orientates that sort of wrap plane. So obviously we can change the view as well. As you can see here that if I move to this side, it'll angle it one way, and if I drop the mouse, it'll angle it the other. So we can just click and drag, and we can drop a wrap around here. It will want to continue, or we can just click an empty space elsewhere and move somewhere else on the part. Obviously, because we've put in a symmetry plane, we can just focus on one side and then use the geometry mirror tool to fix the rest. So let's say we'll create that one. We'll focus around here maybe. So we can just click and drag on that part, click elsewhere to create somewhere new. So again, just clicking and dragging to create smaller sections just to make life a little bit easier for us. And we'll do the same here. And maybe have this intersecting later on. So we have a series of sort of disconnected shapes. So what we can do, for example, is use the bridge tool. Let's say we'll go from this to this. And now that's put in a polynomial shape to bridge those together. And we can even use the bridge tool to join this to this bottom face, to join them up neatly like that. Another thing we can do, so if I come out of the bridge tool, is we can actually edit the polynomial cages themselves depending on what we're selecting. So if I click on just this face, for example, we can change the plane and the size of it. We can rotate around the central axis, and we can even sort of click and drag to extend the shape. If we were to just click on one of the lines, you can see that we have the option to move this line about, so we can sort of stop this plane from being perpendicular to the rest of the part. And if we are to click on an edge as well, we have the same controls for edges too. So plenty of controls within the wrapping tool to end up creating sort of a neater version of the part. So there are plenty of videos we can have a look at using the wrap tool. The advantage of wrapping manually is that you end up with less polynomial cages, which makes life a little bit easier when you want to edit things later on. And so again, please feel free to continue wrapping and manually creating the polynomials for your part. It's pretty friendly to do. More care will be needed when you get to the intersections of these parts, but you can then simply Boolean them together. So there's one method that you can employ when creating the polynomials. And now we'll have a look at another kind. So we can actually, using this part here, we can shrink wrap everything together. So if we go into the polymesh side of things, so again, for slightly more complex parts, we can go ahead and use the shrink wrap tool. So we'll go to shrink wrap parts. We're just going to click and drag everything. Actually, in this case, what we might do is come out of this tool and just hide these, because those don't need to be included. So all you need to do is click on the part and hide it, or you can click on this icon here. So to the left of the part name, you can just click on the icon and it will hide it. So yeah, if we go to shrink wrap, we'll highlight everything and we'll press shrink wrap. So there is the wrap created. We can then right click and swipe out of that, and if we go to convert to triangle mesh here, we can then go ahead and smooth it. So we can see here that smoothing values will either make it more jagged, so low smoothing, or high smoothing. So we'll leave it around there. So once we've done this shrink wrap, we can go back into polynomials and we can actually fit the shrink wrap tool. So if we go to fit, and that should leave us with a polynomials fit based on that shrink wrap. So something that looks a little bit like this. So again, this is another method of creating something close to what you'd like in CAD quite quickly as well. There are plenty of controls within the polymesh side of things. So you should be able to press on the hamburger, value. So if we simply just go to the shrink wrap side and press this, you can choose a voxel size once you choose the part. And the same for fitting. So within fit, we have this where you can choose an element density and a break angle. So if you increase the element density, you'll have sort of fewer parts in there, and a smaller element density, you can have more parts within the model. So there's a couple of ways in which you can go ahead, optimize a part, and then take something back into CAD for you. So a couple of quick ways, really depending on sort of the complexity of the part. So you can either use sort of the wrapping tool, the automatic polynomials fit, or the shrink wrapping. It really depends sort of per use case. But yeah, that's it for performing an analysis, having a look at the optimization and how that compares to your original design. I hope you can see that using the geometry editing tools, you can run through design iterations really quickly, or you can go ahead and optimize the part as well based on that, and see how all these values compare using the compare tool itself. And also another note is that Inspire has a host of manufacturing tools, in sort of including casting and extrude. So if you want to make sure, and including Print 3D, which is even within here as well. So if you want to see how your part is going to perform when actually being manufactured, that's something that you consider as part of your generative design process. So thank you for watching this video, and please enjoy using Altair Inspire for your own analysis and optimization.